Let's see. Question 30 and the question 2019 HCC. So first of all, think about the motion here. When the ball is at the P, okay, at P, you have to know that the total mechanical energy, the E, is always be U plus K, where the U is the gravitational potential energy plus that, the kinetic energy. And according to the conservation of the energy, the total amount of energy will be conserved. It will just transfer and transformed. Does that make sense? Okay, so at the P, let's get the total mechanical energy. What we have there is, as a P is at the stationary, it's not moving. We can straight to say it's half, okay, the formula for that is mgh plus half mv squared. But what if at P, the half mv squared is 0 because it's not moving. So we can just say total mechanical energy is same as the U, which is mgh value. Does it make sense? Okay. Now consider about what happened. The question is you calculate the difference between the height between P and Q. Think about at Q. At Q. Given here. So we can take the velocity of the ball at the Q is 1.5 meters per second. But the total amount of energy still be conserved, which is U plus K. That's the same as mgh value that we have in here. So I'm going to put the H of the P, just in case. Then what we can take here is the total mechanical energy is then mg times height at Q, okay, plus half mv squared here like this. Does it make sense at all? Okay. Then can I just say these two are the same amount of energies, which means mghp is then mghq plus half of the mv squared. You do not need to know the mass of the ball because mass will be cancelled on all the sides here like this. Move that side to here, the mg, the ghp minus ghq, giving us half of the v squared value here like that. Remember the g comes out, then you get the hp minus hq. That's what? Change in the height from the P to Q is equals to half of the V squared. Therefore, the change in height, which is the actual height from the P and Q, is known to be half of the V squared divided by the G. That is half times the V squared, 1.5 squared, times 1 over 9.8. Then you should get all point. Given that sig figs we have, how many sig figs? 2. So your answer must be in a 2 sig fig, which is 0.11 meter. 2 sig figs. Marking, 3 marks. Goes on to whether you use that. So if you get the marquee answer with the 2 sig figs, you get a 1 mark straight away. But it doesn't mean like you just can write your answers right. Working out, showing the P, the mg energy equals to that and that, all the relevant working out, you get the marks.
You have to reference the conservation of energy.
You do.
Like, so you have to make it equal each other.
Yeah. Otherwise, you may use the motion equations if you like to.
Oh no, I just did E initial is equal to E final.
Yeah, that's the same. Yeah, that's basically telling you like the conservation energy too. You can define that conservation energy if you like to. Why not? But even without doing that, you know this is the kind of making sense. Good. A. If you can see the answer, it's kind of makes sense. It's pretty easy and straightforward. B. B is not that straightforward. The ball takes 0.5 seconds to reach the floor after leaving at the track at Q. Calculate the height of the Q above the floor. This is unlike a kind of different like projectile motion. So I gave you like some examples of the projectile motions we can possibly have. One was going like the same level, okay, like an asymmetrical. One is we drop something from that. Okay. Another one was we drop something and launch that from the height given over here like this. Okay. This case, this is kind of like it's not applying. These cases are not applying to that because what we have there is the ball from the track Q is kind of launched downwards. Yep. So you will have a certain angle as well as some distance from here. So what we can think about the trajectory of the ball is it will trajectory, it goes like that. With having the initial velocity of 1.5 meters per second with the angle to the horizontal theta. Okay, now this is why you're given the angle of the 50 degrees to the horizontal. That's theta. It's actually the 50 degrees. Then you need to construct the vector diagram again that we have a u which is going in this direction. And that is the theta. So we still have uy and ux. Okay, what the ux is u cos theta, uy is u sine theta, their value too. But one thing about this is what I mean. If you know you have a downward direction here, you should know this must be the negative u sine theta. Does it make sense here? Because what we're going to take here is we take the ay to be minus 9.8 meters per second squared. You're going to match that direction too. If you put it in the positive, you won't get the same answer as me. Does it make sense? Okay. And then what we do is we're going to apply the same rules. What we are given there is it takes 0.5 seconds. The time taken is given. So t was given as 0.5 seconds given here. Then use this. Sy is equals to uyt plus half ayt squared. Does it make sense? Let's substitute all the values in. Uy is minus u sine theta. I'm just going to write that 4.9 t squared. So let's see. U was given as 1.5. So I can just minus 1.5 times sine 50 minus 4.9 times the t square value is 0.5 square here like this. See that? If you didn't put the minus value here, you get the positive, you get the shorter height than me. Then the total displacement would be, we found from there, the calculator must be 1.8 meter. Well, the displacement minus 1.8 meter, therefore the height from Q is 1.8 meter. That's the final answer then. Okay, that's kind of trick that you have to use, and the question didn't really you twist it unless accept the minus vector there. Make sense? Again, 2019 HSC. I didn't make the question. This is actually made by HS the makers, and every year projectile motion, we always get the projectile motion question, at least one question in your short answer or the long response. Marking goes from the 2 to 4 marks to 6 marks. And Band 6 students, they do not lose any mark from the projectile motion because this is the first chapter of the year 12 physics. Any questions about these? Everyone good? Two suffix. Because we're given the two suffix there. Oh, 0.5 seconds. 0.5 seconds. This is something I hated about. I would take that to the, that's approximately 2 meter into 1 sigfig then, following to that sigfig value that we have. They do. But make sure you show that the relevant working out here. Don't just write straight to the 2 meter. Write the 2 sigfig or some relevant values or the extended value, and then write it matching to the sigfig that you're given. That's a safer. Any questions about this HSC questions, guys? Too easy or too hard? So the question in HSC, or not even for the HSC, because we had that question in 2019. Guess what? In 2020 school assessments, we started having these type of questions in school assessment too. So if you want to see the trends on your school assessments, it's good to see in the previous year's HSC past paper, because school teachers will read that paper and think about how we get train students for the upcoming HSC examination in next year. Okay, so I give you something unrelated question. But last year the projectile motion question is so easy, so this is kind of one of the hardest questions that we had in HSC. All right, please open your workbook. We're going to move on to chapter 2, which is the circular motions. We probably finish up to the chapter 3 today, which is all related circular motions there. So page 30 of your workbook, please. So let's talk about some uniform or just the circular motion. So when we say the circular motions, obviously it's a movement in a circle. Okay, but I want you to imagine about when you're running a track, okay, or when you're in the roundabout and when you're driving, you're not driving, but when you're running a bicycle, okay, you try to run, you're running and making a circular motion with your body, like you make a turn. That's a circular motion because I'm at a turn. But I want you to think about what forces, what are the kind of forces you apply on your body. To make a successful one turn, I need to apply the force on my right leg so that I can turn right. It's very simple. If I turn left, I put a force on the left leg, turn left, making circular motions like that too. So this is related to the Newton's second law that we learned in module 2. Remember that Newton's second law is not just the F equals to ma, it's more about the net force in here. But remember one thing, in any circular motion, I don't care about whether that's in the planet levels or the sun's orbiting, in any of the circular motions, the net force is always the same as there's something called a centripetal force. Now, centripetal means that the force towards the center. This simply means that there is always a net force applied towards the center. This is the golden rule to remember the circular motion, solving any type of the circular motion you will have. It simply means that, in short, I can write it down like this. The net force in circular motion is same as Fc, that's related to centripetal force, which is found by mv squared over r. That's a formula that you can memorize. But let's think about why is that. This is also the same as, by the way, Newton's second law, ma. Therefore, we can say centripetal acceleration, or AC, is also be the v squared over r. I give you the answer. This is the answer for every single circular motion questions. But I want you to think about why here. So let's think about the acceleration then. Daniel, how would you define the acceleration? Change in velocity. And velocity divided by change in time. Thank you. I shouldn't ask you. Okay. Okay. In other words, I can find it by delta v on delta t. Something you learned, that's acceleration. It is called that. That's what we learned in module 2, module 1, for many times too. Then let's talk about what it means by change in velocities again. Or in how many circumstances we can have the change in velocities?
Like if you speed up.
Speed up from so you're speeding up. So there's a change in velocity.
Yeah,
what about speeding down?
As well.
There's a change in velocity. Don't just think about acceleration as speeding up. If you think about overall definition of the change in velocity as if there's any change in the velocity, we would take that as acceleration. That's how we define the acceleration in physics. We do not define the same way in real-day life. When we say acceleration in real-day life, we simply mean speeding up. But in physics, we define the acceleration as there's a change in velocity in any circumstances. Means that there's a change in the magnitude of the velocity. For example, as you said, from that 10 meters per second to east to say 5 meters per second to the east. Remember that we are talking about velocity, which is the vector. You must talk about the direction. Without the vector, it's just a speed. Whether that be that or from that to 15 meters per second to the east, we say this is change in velocity, but we did not change the direction. Make sense? Okay. What about second one? We can also have change in the velocity by change in the direction only. For example, same speed, 10 meters per second to the east. Now change it into 10 meters per second to the west. Steph, can we say these two are the same vectors or same velocity? When I say, oh, you're moving in 10 meters per second to the east compared to 10 meters per second to the west. Are they the same velocity? Why? You're saying that, hey, if we're moving in 10 meters per second to the east, you will get to the same displacement, same position as if you're moving in the 10 meters per second to the west. Will you? If you move to the east, to the west, will you get the same destination? No. So can we still say they're the same velocity then? They are not the same velocity because velocity again is the vector which is defined by both of the magnitude and the direction. Guys, study this. Study this. This is year 11 contents again. That means if we change the direction from east to the west, there we assume that there's change. It's not assumed. There must be a change in the velocity. Is it clear to everyone? Third is change in the direction. In the magnitude and the direction both. So that means from 10 meters per second to the east, now we're moving in 15 meters per second to the west. Yes, both of the magnitude, how fast you're moving, and the direction are changed. So there must be a change in direction there, and the change in velocity. Okay, then let's think about uniform circular motion here. For the circular motion, we believe that we have putting something there, making a circular motion like this. Kind of like, okay? So, from here, let's think about the initial and the final velocity if the ball is located here, in the halfway. Okay, so still attach the ball on the string and go like this. Initially, okay, guys, think about it. Initially, the ball was moving to this direction. That's U. That's a U given here like this. Okay, and I take this as a final velocity V. Can you see that? Okay, Kevin, can I say these two are, if the U is given like the same magnitude, say that's moving in 10 meters per second, and V is also still moving 10 meters per second, because when you're rolling something, the mass is kind of moving at the same speed. But can I still say they're the same velocity? No. What can you tell me of direction of the U? This way, which is to the right. What about V? Down. So we can't say these are the same velocity, even though they have the same magnitude. Make sense? Make sense? Then can we say, oh, there is some change in velocity? Yeah? How do you find the change in velocity? It's found by V minus U, the final minus initial. Yep, but we cannot minus the right and down. This is why we need to use the vector diagram again. How do we use the vector diagram? We know when the V minus U, if this is this is U vector, okay, the minus U vector is this, the opposite direction there. Okay, V is simply going down, that's a V. So weighting these two up, the rule is head to tail, then tail to head again. So U minus U is added to here like that. Can you see? Then resultant vector is this one. That's called the V minus U, the resultant vector, which is known as delta V again too. Does it make sense? Okay. So I got the delta V is somewhere in the middle. That's a delta V. If this is moving in a certain time, obviously it's moving in a time, can we get the acceleration? I think we can find the acceleration from here too. Then what we can take account from here is think about the magnitude, guys. U and the V has the same magnitude 10 to 10 because they're moving in the same speed over here. So what we can take here is the magnitude v minus u, or delta v, is founded by square root of the u squared plus v squared, isn't it? Okay, but as we can just considering about the magnitude here, as u, v and u have the same magnitude, can we just take that as the v here? That means absolute v is equals to absolute u in terms of direction. You can neglect the direction there. Can we just think that as that's same as 2v squared? Okay, giving us root 2 times the v here like that. Okay, or we can ignore the time taken here. This is kind of giving us that v squared value too. So this is the kind of idea to get the centripetal acceleration, that we get the change in velocity which is giving us that value, but don't worry about this kind of calculation there because it's a little more complicated. It's also described on your next page, given over here. Sorry, not the next page. Given on the page 34 and 35 there, giving you that the time taken over here. But I want you to just understand that the acceleration is not only be speeding up, we are dealing with a situation where there is no change in the magnitude, but we are constantly changing the direction, because when we take account of the motion of the ball in the circular motions, it's always changing the direction there. And what you see there is, that's called the linear velocity, v, which is linear velocity, is always what? Tangential to the circular track, which means they're making a 90 in all the times. And in any of the times given here, if you think about here, we get the acceleration changing v towards the center in every circumstances. Considering that when you're minusing these two, yes, you get the change in velocity given here too. So this is how we get the in a circular motion, we always get the acceleration towards the center. We call that centripetal force. And remember that in circular motions, in any circular motion situation, the net force is always the centripetal force that we have. We're going to do more questions related to that. So let's have a look at something, a basic year 11 question. Page 31, please. So the average velocity, that's how we get the of the object at the end of the time t, depends upon the magnitude and direction of the object's displacement from its starting point at the time. So v of the as, you can copy this down, especially for the circular motion, because we are thinking about circle there. Can we think like, the average velocity is same as the total circumference of the circle divided by the time taken, which means if I have one circular motion there, if that's having the r, this giving us this, that means that total, this one circumference and divided by the period, where the period t, capital T, is known for the time taken for one revolution, one circular motion. That's called the one revolution there. So we can just put it there like this. One circumference can be found by 2 pi r. Too simple. Okay, that divided by the t. That's how we get the average velocity, also known as the linear velocity, which means that in this circumstance given over here, in any of that situation, that you will have the same magnitude of that 2 pi r over t. With the capital T, guys, remember that capital T stands for the period only. Do you remember the wave formulas? F equals to 1 over t, that's one period. We're still using the same concept here. All right, so let's have a look at the questions related to that. 2.1. A wind turbine has a blade of 55-meter length that rotates at the frequency of 20 revolutions per minute. At what speed do the tips of the blades travel, and express your answer in the kilometers per hour or seconds. Okay, let's have a look at that. So 2.1, started with all the given information that we have. We're given that blades has a 55 meter length and rotates frequency. So we're given that R, which is the length of the blade, or the same as the radius of the circular motion is 55 meter. That's given. Okay. Now, it has a frequency of the 20 revolutions per minute. Now, as we need to find in the hours there, we can just change the time. This is saying that 20 revolutions is per minute. Okay, just think about here. If it rotates 20 revolutions per minute, simple math question, Steph. If that rotates at 20 revolutions per minute for an hour, how many rotations would it have? Which is 20 times 60, because we know in 1 hour we have 60 minutes, which is 1,200 per hour, revolution per hour.
Why are we making it 2 hours?
Because we have a unit of the kilometers per hour there. Okay, or we can even use for the per seconds. If we have a 20 revolution per minute, means that 20 divided by 60 revolutions per second then. Does it make sense? Okay. Now, what we have to use there is, to remember this, frequency is known to be 1 divided by the t. That's from module 3, by the way. We can use the same formula here. Frequency is how frequently it moves in the per seconds. How many revolutions we have in per seconds. In other words, we can find the time taken for the 1 revolution by inverse of the frequency. So t is equals to 1 over f. That is giving us, I'm going to use the seconds or even that over here, doesn't really matter. For the 1 revolutions, it's got to give us this. It's going to be 60 over 20 the seconds. That's giving you 3 seconds then. Which makes sense. In every second, it completes 1 revolutions in every 3 seconds. Does it make sense? Okay. After you got it over here, you got to use this. We're going to think about the v, the linear velocity, is found by 2 pi r over t. That's giving us 2 pi times the r, which is 55, divided by 3. Okay. Now, turn your calculator in the radian mode. You need to use a radian later on too, because but make sure you switch that to degree later on too. The 2 pi times 55 divided by 3, you would get 115.2 meter per second. This is how fast the turbines, or the wind turbine is rotating now. Not done yet. How to convert the meters per second to kilometers per hour? 3.6. Yes, I'm glad you remember that. Okay, that is in the kilometers per hour. That's the same as divided divided that by 3.6. You get 32 kilometers per hour as an answer then. So the point is, okay, you don't really need to find this point over here. Just focus on to the period. To find once you get the period value, you should be able to get the linear velocity of the turbine or any of the circular motions that you have. Okay, now, could you try for the next one then? The water wheel question.
T for the period? Why is it like T cycle period?
You asked me the same question, why the V stands for the velocity.
I mean, yeah, because it's starting with V, so.
Yeah, but period is like the longer period of special T, special time. This is why I give it a capital T rather than with small t. With small t is generally giving you any of the times. We only use the capital T for the period, by the way. That's because that's very special time. Okay? And the unit for the period is always be the seconds, not in minutes or hours. It's good to remember this one too. Finished? Okay, now we have a frequency which is given at 10 revolutions per minute. Make sure you convert that unit to the revolution per second so that we can get the periods from it. This is give same as 10 divided by 60 revolutions per second. Think simple, guys. Okay, if that rotates 10 revolutions, 10 circles in 1 minute, for the 1 second, you can just divide it by 60 seconds there. Does it make sense to all? Okay, then you get the t, which is the inverse of the frequency. That's giving you that 6 seconds. Then, easy to get the answer. The velocity is 2 pi r over t. That's giving you 2 pi times 2 divided by 6. You get the 4, 3 on 2, whatever. Okay. So 2 pi divided by 3, you get 2 point. Given the sig fig, how many sig fig are we given? 2 sig fig. So 2.1 meters per second. Do we need to convert that into kilometers per hour? Yeah. We do. Okay. So this is equivalent to the divided by 3.6. And so all 0.6. No, 0.58 in 2 sig figs. Okay, 2 sig figs given. Yeah. Make sense to all? All right, that's how we get the linear velocity. Then next part is, let's talk about the angular velocity. So linear velocity versus angular velocity that we have. Now, linear velocity simply means you can think of linear. So that's unit is given a meter per second. And I want you to think about what do you mean by meters per second. It simply means we can interpret it as in every second, okay, an object moving in a certain meter. That's how we can interpret the meters per second. If you have 10 meters per second, in every second it moves 10 meters. Does it make sense? That's how we interpret the velocity or the speed unit. Now, angular velocity, I'm using kind of similar, but slightly different. Angular velocity is defined, a unit is degree per second or the radian per second. So for example, if you have 10 degrees per second, it means it moves 10 degrees for every second. So this is how we define the angular velocity. So we're not considering about how far it moved in terms of the distance. We are considering about the angle it moved. So, or 10 radian per second means 10 radian for every second there. That's how we define the angular velocity. So in short, angular velocity is known as the symbol of the omega or W. Is founded by delta theta divided by delta t, where delta theta means that change in angle divided by change over the time. That's what's given in your formula sheet. Okay, so you can just write it as angular velocity is equals to change in angle divided by change in time. Does it make sense to all? You're just counting like how fast is changing the angles per given time. If a faster, think about a faster rotation, it moves fast really fast, then the angular velocity must be high. But let's consider about the relationship between linear and angular velocity. If an object is rotating really fast, like this, okay? can we say, oh, you know, this object has a really fast linear velocity, as well as angular velocity too? Because an object is moving really fast, it's covering, like making a fast revolution in a shorter period of time, as well as it's changing the angle really rapidly. So there must be some relationship between linear and angular velocity. In other words, when the linear velocity increases, the angular velocity also increases too. It's kind of obvious. I'm making a really obvious thing here. It's common sense. But let's use the common sense to derive into mathematical formula, which will not be given in your formula sheet. But I want you to use this. It's very important, guys. You will not given this formula in your formula sheet. Sometimes your school teacher will not teach you ever. But we still have questions in the HSC. All right, let's think about relation between over here. What we know is the velocity v is known as 2 pi r over t. That's given. Now, for the 1 revolution, shall we think about here? The angular velocity can be measured in this way too, which is known as delta pi, or delta theta and delta t. Yep. Ryan, for 1 revolutions, if we start on 1 here, completed 1 circular motion there, what would be the change in angle for 1 revolution only? 360, which is 360 degrees divided by, if we take a time for 1 revolution, what is this? That's for the period, isn't it? Which is same as 360 degrees divided by the t. But if you ever learned in the mathematics, we do not use the degrees for the circular motion or any circular, and it's like a circular geometry. We rather use the radian. So 360 degrees in radian is 2 pi. Thank you. Ah, I have that in here. Can I just substitute back in here? Which makes v is therefore 2 pi over t times the r. That's what? The omega times r. Therefore, giving us the value is either therefore linear velocity is the product of the angular velocity times the radius, or angular velocity also be v on r like this. And if you think about it, guys, it makes sense. It makes sense because if you really increase the radius of something turbine, okay, even if you have the same velocity here, it's harder to make a change in angles compared to shorter, or compared to like this small circles and big circles there. Okay, this is the formula that you must memorize, which will not be given in formula sheet. This is not given, but you can use that. And there's a big difference with like by knowing this or not. Some of the questions like this one here. All right, let's see. 2.2. A wind turbine has a blade of 55 meters in length that rotates so that tips of the blades T travel a distance of 150 meters in 2 seconds. At what angular velocity does the turbine rotate? Express your answer in degree per seconds. Okay, let's write it down, all the relevant information that we have. We are given that the R is given at 55.0 meter in the 3 sigfigs. Okay, the time taken for travel the distance 150. So we're given the distance S is given at 150 meter, and time for that is given 2 seconds. From here, we can get the velocity. Linear velocity equals to just the displacement divided by time. That's 150 divided by 2 seconds, which gives you 75 meters per second straight away. Yep. If you got it up to here, then you have to question that, oh, how are we going to find that angular velocity? If you know the formula, that angular velocity is what? The v over r, you can just show the substitution straight away. 75 divided by 55, that's it. In giving you, this is actually giving you in the radian, so 75 divided by 55, it's giving you 1.36. Guys, this is something not in degree yet. This is giving you the radian per second. Then how do we convert that into degrees? Anyone? from radian to degrees?
Times 180 over pi.
180 over pi. There we go. So 180 divided by pi. Do that, then you get beautifully 78.1 degrees per second. That's how you can get the answer. Does it make sense? Or you can think about it here. Oh, it moved a certain circumference, like in a partially, about 150 meters. So the angle must be related to that. But rather you think of it complicated, like you just use that. I'm trying to help you. I'm trying to make your job easier using this. Rather than think about, oh, it moved 150 meters in circumference. I should calculate the angles for that too. It's actually more complicated. Make sense? Easy. Try next one. Okay, the truck wheel of the diameter 1 meter travels over the 8 meter of the ground in 3 seconds. What is the angular velocity of the wheel? Express your answer in degree per seconds again. So we have a diameter 1 meter. So diameter is given 2r with a diameter is given as 1 meter, giving us that r is then simply 0.5 meter from it, and over 8 and given that s, the displacement it traveled was 8 meter given. T was given at 3 seconds for that given the displacement. From here, we come to V is equals to S on T. That's 8 divided by 3. I just leave that to meters per second rather than we find the exact value. So I mean, they leave the exact value in the fraction forms. Okay, once you get up to here, use the formula. Omega is equals to V on R. That is 8 on 3 times that. The R value, 1 over 0.5, which is times 2, similar thing, same thing. So 16 divided by 3, it gives you 5.33. Remember, this is still giving the radian per second yet. So to convert it into the degrees per second, times 180 divided by over pi. There we go. And did you get what? It should be in the degree mode, by the way, so you should be given at 305. 305 degrees per second. Given that 1 sig fix, that's same as 300 degree per second in a 1 sig fix. Okay, guys, just think simple here. Use your common sense. If something moves faster in the circular track, obviously you will have the greater angular velocity because changing the angle so fast means that in every second, the truck wheel is rotating about 305 degrees in every second. So almost like one period. Does it make sense to all? Okay. All right, I kind of talked about centripetal acceleration, so given that, let's kind of explain that. All right, using this, page 35, please. Using the idea about a linear velocity and relation to the that, we can get a relation here like this. We don't really use it quite a lot, but as we know, c, the angular velocity, the centripetal acceleration is bounded by v squared over r for circular motions too. We can substitute the v is equal to 2 pi r over t into here. Then you get the AC becomes to 4 pi square r over t squared. But do not remember this. Do not memorize this one. Okay. You need to use that in a certain circumstances. You have to use, but it's pretty easy. If you just can remember that the v is this, okay, and a is that. Show the substitution. That's all you need to do. So when do we use that? We use the questions like 2.3 given over here. Let's go through this together then. What is the centripetal acceleration of the hammer that is swung in a 1.7 radius circle if it makes 0.8 revolution in a second? So let's write it down what we have in the given formula there. We're given that radius is 1.7 meter, that's 2.3. Okay, and it makes the 0.8 revolution in a second. Frequency is given 0.8 revolutions per second. That's given. So to find the period, t is equal to 1 over f, that is 1 over 0.8, which is b 8 simply. Isn't it the 8 seconds? Yep. Then once you get up to here, it's kind of complicated to find acceleration. Or we can find acceleration from 2 pi r over t. Yes, you can do that. But rather you do this. Or you can think about it. 1 over 0.8, isn't it? 1.25, yeah. It's the other way around, 1.25 seconds. So you can think about it. V is equals to 2 pi r over t. That's and that's 2 pi times the r, which is 1.7 divided by times 1.25. You can find some of the value, and a is known to be v squared over r, given over here like this. You can just substitute the values in. That's given as 2 pi, 1.7, and 1.25, and square that times the 1 over 1.7 there. Well, you can cancel out 1 over 1.7 if you like to. If you expand that, then you'd get 4 pi square, that's 1.7, but a 1.25 square like this. Yep, the 1.7 will be cancelled because it's square and we have 1 in here. So, time to use your calculator, 4 pi squared times 1.7 divided by 1.25 square. You should get 43 meters per second squared for the acceleration in 2 sigfigs. Now what would be the direction of the centripetal acceleration, Andy? What would be the direction of the centripetal acceleration? Direction. What would be the change in the velocity? It's always, yes, towards the center. Remember this phrase. In every centripetal, I gave you the hint, centripetal means towards the center. In centripetal acceleration, the directions are fixed into towards the center. Okay, remember this, we are minusing the v, u, and the v for the motion of the ball. Okay, v minus u is always be this v minus u. Then what do you get? Always to the center. That's delta v. Do you want me to show the different situation there? Okay, we have this u and that's v. So the ball is moving into this direction there, in circular motions. Yep, same. V minus u would it be v minus u? That's a minus u, isn't it? Okay, so that's towards the center too. So it will actually move towards the center. So you can always get the same direction, which is towards the center in this case, for every centripetal of accelerations. This is how we use the vector diagram, which we learned in module 2. Module 1, actually. All right. Centripetal force is kind of similar concept too, so we can talk about that as well. Could you answer the question 2.4, please? It's simply using the acceleration, use that. Remember that every centripetal force will also have the same direction as centripetal acceleration, which is towards the center. So if you get any question related, like find the force, find the acceleration, you must write the direction as well. So what I mean by the hammer throw events is, if you ever watch like the Olympics, it's like basically holding the hammer and hold like this. That's how you do the hammer throw, and you basically release the hammer. So from that centripetal force, you get a lot of velocity. So as you get more acceleration, greater linear velocity, and you can relate that to a little bit of the projectile motions too. If you release that with a more greater, faster speed, then you expect that the further the distance you would get to. Okay, so from here, that's actually using for this something we know as the slingshot effect. When you're launching the space probe to the further distance, we use a gravitational force to make a circular motion and release that, so that we can achieve the highest, the fastest speed. Now, this is something given here. It's a hammer throw event. The ball or the mass is given as 7.0 kg. In a horizontal circular path, the ball is moving at 20 meters per second. Okay, so velocity is giving us 20 meters per second at the radius of the 1.6 meters. It's all given. Okay, what we get from here is we can the acceleration or centripetal acceleration can be found by v squared over r like this. Or we can just think about Fc, which is centripetal force, is known to be mv squared over r as the F equals to ma. Does it make sense? Okay, so or we can say Fc is equals to m times ac. That's the same thing. So what we get, mass 7 kilo times velocity 20 squared divided by r 1.6. That's all you need to do. So 7 times 20 squared divided by 1.6, you to get 1,750 newtons. Again, magnitude only, sorry, the acceleration. Did I find the force eventually? Yeah, okay. That's today. I'm sorry guys, didn't read the question properly. That's giving us 20 squared divided by 1.6. So 20 squared divided by 1.6, giving you 250 meters per second squared, which is units. You do not need to worry about the direction because the question asks you the magnitude only. That's it.
I consider like F equals ma for the FC equals the
Yeah, but it's the same thing. It's the same thing. Why would you do that if you know that? The tensor force is the answer for the question B. I accidentally found the answer for question B.
So if you find the direction, you did just the vectors.
Good question. What about the direction of the centripetal acceleration then? Centripetal, centripetal, centripetal. Towards the center. Always the center, towards the center. Okay? So you don't have to worry about east, south, north, or left and right for the centripetal. It's quite clear and it's given by the word like centripetal there. Now, next question. There's kind of similar questions there. And easy questions. Athlete, the 7 kilo in the 25. Okay, guys, don't worry about this question. It's exactly the same. We changed the value. So kind of easy question you don't have to worry about. Rather, I want you to try the question 2.5. Question 1, 2, please. Now, this is the time you need to think about a little more about mechanics or Newton's law. I want you to think about what about action and the reaction force. It's not a centripetal question, by the way, the circular motion question related. It's more a year 11 question. Okay, what is the questions one related to? Phil is standing inside the tram when it started off suddenly. Len, who was sitting down, commented that the Phil was thrown backwards as the tram started moving. Is this a correct statement? Explain in terms of Newton's law. What law? This is Newton's first law. They're stating that an object will move in the same motions unless or until like affected by the external force. Or don't mix use the law of the inertia, guys. Newton's first law is not the law of the inertia. The law of the inertia is a part of the Newton's first law. We use the terms inertia because it explains the Newton's first law well. Inertia means what? It's the tendency of the stay in the same motion, tendency of the staying in the stationary. Okay, so now you all have the inertia because you're sitting down. But if you think like because you're carrying the mass, you must carry the inertia of it too. Now thinking about the Phil's case, if the Phil, not the Len, sorry, it's a Phil standing inside again. The Phil was standing here, so Phil had inertia, or Phil had a tendency to be stationary before this tram suddenly moved. Now when tram moved forward to the left-hand side, because the Phil had a tendency or the inertia to be stationary on the same spot, it feels like he moved backward. Okay?
Is it okay if you say the external force of the tram displaces it, which causes inertia?
No, inertia will be carried by the Phil every single time. Because of the inertia, it's not the inertia exerted. Because of the inertia, he's moved back. It feels like he's moved backward, but eventually, it's actually Phil just try to stay the same spot. It is the tram moved forward. So if the Phil's try to be on the same spot as before, while the tram's moving forward, it seems like the Phil's kind of moved backwards. Does it make sense? But if you think about the position of the Phil, his B stay in the same ground. He didn't really move. Okay, that's what you get. Same for like when the tram or bus is suddenly stopped, because when the tram is moving forward, you have an inertia moving forward. You're keeping that of the motion. But when the tram just stopped, because you're containing that motion of moving forward, which is inertia, you try to keep that motion forward so that when the tram suddenly stopped, what do? You kind of flying forward because you keep that inertia of the movement. Does it make sense? Okay. Think about inertia as like kind of tendency of the resisting or tendency of the maintaining the motions that it has. In this case, when you're stationary, you have inertia of the stationary. Okay. When you're moving forward, you have a moving forward inertia. Does it make sense too? Quick revision on the year 11.
He went back.
In this case, he went back. But I'll just give you a different situation. When tram was moving and suddenly stopped, the passenger will kind of move forward, because all of the passenger would now have the inertia of moving forward.
So like inertia is not relevant in this case.
It is relevant. It's going back because it had an inertia of the being stationary in the same spot.
Yeah.
Does it make sense? It seems like he's going against to that because he had inertia of staying same spot. If you like to think about it here, you try to be stationary as much as you can. Okay? And by suddenly something moved, but you want to keep that position there, everything else is moving forward inside. But you try to be that. So you'll be like, see that? My legs moving forward while my upper body is staying back. Yeah? Does it make sense? So it feels like for the others, in your perspective, I feel like I'm kind of falling backwards. Because I'm keeping that position over here whilst my feet is going forward like this. Make sense? All right, question 2. Explain why the normal force Fn and the weight force Fg are not an action-reaction pair for the Newton's third law. State the third law pairs of the marks sitting on the table for both Fn and Fg. Okay. The normal reaction force, the Mix constant normal reaction force is normal means that 90 degrees or perpendicular. So you must say, or I should say perpendicular. The reaction force. Yes, when you have the mug sitting on there, okay? There is a weight force applied from the center of the mass, weight, okay? And there's a reaction force which is working perpendicular to the surface and moving upwards there. Because if we have a weight force, it means that you have a normal reaction can be applied. Yes, it seems like they are the same because we see that net force is 0. It's not moving. It's stationary. So there's no force acting on this mark. Make sense? Means giving us that the N plus minus, that's mg by the way, minus mg. Why I put the minus? Because that is the negative direction. Move that, you get mg equals to n. It seems like it's true for the plane surface. Well, what if we have slant surface like this? What if the table is kind of moved and you still have a mark there? Can we still say the normal reaction force is the same as the gravitational force? No, the normal reaction force following the definition would be go like this. Okay, if that makes a certain angle there, time to think about here, mg, you get the two components of the n. One is going upwards, and going down over here. So that's n of the y and n of the x. Where n of the y, that's the angle theta, that's the same as n sine cos theta. And because they're not moving perpendicular here, we can take, in this case here, mg. I'm not going to go too much details, but I'm just giving you Fy net force of the Fy equals to 0, giving you that n cos theta plus minus mg is a 0, therefore mg is equals to n cos theta for this case here, which is not exactly the same to the normal reaction force. So it is not, for this situation, yes, it is the action and reaction pair, but in here, it is not the action-reaction pair. And the reason why we can't say the action and reaction is because you always get the gravitational force. It's not action sometimes. You get a constant force applied on your body. Does this make sense? Okay? So kind of thinkable questions. All right. Before we have a break, I would like to try the question 7, please. Jack and Jill are playing on the merry-go-round at the playground. The merry-go-round has a radius of 1.2 meter. Jill pushes the outside of the merry-go-round at a distance of the 5 meter. Okay, so it's given that question 7a, that you're given the radius of the merry-go-round is 1.2 meter. That's given. Okay. It moved the distance of the 5 meter given over here. So we can think of it here. If the merry-go-round, the top view is moving to this distance over here like this, move that total of the 5.0 meter. That's S is given as the 5.0 meter given. Yep. So considering that we have a radius here is 1.2 meter there, think about a relation between over here. This is partially some angle. So you can think of this a bit of mathematically here. The theta over the 2 pi is basically to find the length here, 2 pi r times that to the theta on the 2 pi. That's we can get the radius. That's giving you the partial s or the L. Does it make sense? Because one circumference, it takes a 2 pi r. Okay, if you think of this from partial angle, so that's a 2 pi, we're given this. So cancel this one out. We get the r times the theta is giving you the displacement or the L. I should just throw s here. Does it make sense? Yeah. Okay. With r, then we're given the 1.2 meter. that's given also times that, so I just substitute the value. 1.2 times the theta is then equals to 5. Therefore, the theta is 5 divided by 1.2. In the radian, by the way, so 5 divided by 1.2, you get the 4.17, or given the two sig figs, 4.2 radians.
Yeah, that's fine.
But in degrees times that to the 180 divided by pi, you get the 238 degrees, which is 240, should say, 240 degrees there. Wow, this is crazy actually. Does it make sense to all? Okay. Oh, I'm using a bit of a mathematical approach here too. L equals to like, L is equals to the pi times r. You can use that too. All right, that's A. B. What is the angular velocity of the, if it takes Jill the 0.5 seconds to travel 5 meters there? So you're given that change in angle is given as, they're going to find it in the degree per seconds, or it doesn't really matter. Change in angle is given as 4.2 radian from question A. The time taken is given as 0.50 seconds. Therefore, angular velocity, which is delta pi on delta t, is found by 4.2 radian divided by 0.5. That's giving you basically 8.4, the radian per seconds. You can find it in degree per seconds if you like to. So that'd be 480 degrees per seconds. So it's really fast, by the way. In 1 second, it rotates kind of crazy. Like, oh, what the hell is he thinking? Like, try to kill someone inside. All right. Jack helps Jules to push Anne to travel at angular velocity of 50 degrees per second now. How long does it take to 5? Kind of pushes Anne. They travel at the angular velocity of 550 degrees per second. Am I missing something? 5 divided by 1.2. Yeah, I'm right. Okay. How long does it take to do 5 revolutions? So given that angular velocity is now new is 50 degrees per second, guys. Okay, think about what I mean by here. In per second, it moved to 50 degrees. Yeah, so for 1 revolution, which is equivalent to 360 degrees, you can think about how long it takes. So the time taken, the t, is then the angular velocity times that, the given the angles there, or yeah, so t is equals to the delta pi divided by delta t, the angular velocity, I'm sorry, which is for 1 revolution 360 divided by 50. So that's giving you the time taken to 7.2 seconds. Which means if they're moving in 50 degrees per second, it takes about 7.2 seconds for 1 revolution. Okay, now we have how long does it give 5 revolution? For 5 reps, it would be 7.2 times 5. Gives you 36 seconds in total. Yep. Does it make sense to all? Yep, that's how we can solve the question related to the angular velocity. Right, let's have a break. We can go to the bathroom, have some water, and come back in 5 minutes. We're going to go through some chapter 3 after this. Okay, question 1. Convert the following angles to the radian. So converting the angle, remember that from the degrees to the radian, what we have to do, we have to times the, it's either be like a 1 over 180 times the pi, or same 1 over 360 times 2 pi, the same thing. Okay, so for question A, for 30 degrees, for example, if we convert that to radians, it would be 30 degrees divided by 360 times 2 pi. They're giving you that pi on 6 radian, which is a pi on 6. Or you can get some exact, some decimal point, doesn't really matter for this. In the same manner, you get the question B answer, pi on 4. See, 60 degrees is known to be pi on 3. Or just take the pi is equivalent to the 180 degrees Celsius, 118 degrees. That's the easiest way to think of the radians. It's more math questions rather than physics yet. D is pi on 2, and E must be 150. That is 5 pi on 6. F, that's a pi. And G, 300 degree is equivalent to 5 pi on 3. And then lastly, H, that's of 8 pi. Okay, for the radian, guys, you do not need to provide in the decimal points, just leave the pi as it is. Now, that's 1. 2. Convert the following angles to degrees. To convert angles now to radian 2, from the radian to the degrees, what we have to do, it's got to be opposite. So you've got to think of a radian time pi on, 180 times on the pi. That's all you need to do. So A, if you converted that into 5 pi, so 5 pi on 5 times the 180 divided by pi gives you 36 degrees there. Okay, same method for the rest of the question. You get 135 for the B. C is a 50. And D, then you get 540 degrees. E is 1,350 degrees, so on. Easy? Okay. 3. Convert the following angular velocity to radians per second then. So, given that the radians per minute, a radian per minute means that we have radians per 60 seconds. So, convert it into per seconds. It would simply be 10 divided by 60 gives you that 0.16 radian per second. Remember that radian per second is a kind of standard unit we're using in physics. So rather than degrees Celsius. B, that we have the 2 radians per hour, so that would be 2 divided by 60 minutes and 60 seconds. That's giving you the times 2 degrees, by the way. Then convert into the some units. It's actually giving you this 5.5 times 10 to the power minus 4 radian per seconds. C is basically we have the 180 per seconds, 180 degrees per seconds means it's converted into the radians straight away, so you get the 3.14. That's actually the same. 3.14 times radians per seconds using that method again. The 720 degrees per minute. That's equivalent to 720 times 2 pi. Now 60 times 60, 60 divided by the per minute, so it's giving you the 4 pi. That's a 3.14 radian per second as well too. E, 1 revolutions per second. Okay, what do you mean by 1 revolutions per second in terms of radian? 360 degrees in radian, that's 2 pi. So 1 revolution is same as 2 pi on the time given, or the period. That's in the per seconds. It's giving you seconds. So it's giving you what? The 2 radian. Or like, so it's just 2 pi or 6.28 radian per seconds. Now, when we're taking the radian per seconds, we do not values into the pi, rather we give it in some decimal points. Because that's giving us a more better idea about the angular velocity. What about 60 RPM? 60 RPM, revolution per minute. That means 60 revolutions per minute, isn't it? So it means the 60 revolution times 2 pi, converting into minutes to seconds, 60 seconds there. You see the 60k cancel, it's the same as 2 pi. That's basically 6.28 radian per seconds, as pi is a 3.14. G is at 300 RPM, 300 revolutions per minute. Same, 300 times 2 pi divided by 60 gives you 5. So 10 pi is 331.4 radians per second. That's the answer. Yes?
So I think D,
Oh, 3,000, sorry.
well, question D.
Yep.
On the 700 degrees per minute.
Degrees per minute. So, shall we go in this way then? 700 degrees into the radian. How do we convert in radian?
4
So that's basically, yeah, so 4 pi by dividing the 2 pi. That's 4 pi per minute. Let's convert it into seconds and 60 seconds there. So 4 pi divided by 60, you get a different value. That's it? Okay.
0.209.
0.294. So answer must be wrong. Okay, 0.209. 209 radians per second in that case. Good. 4. A stone on the end of the string is wheeled in a circle of the radius r at the angular velocity w, omega again. Calculate the tangential velocity or linear velocity in each of the following cases. Remember that we're going to use this formula question 4. The velocity, linear velocity is r times the omega. That's all you need to use. Okay, again, this formula will not be given in your formula sheets, so sometimes you have to use it by your own. So A, using that again, the V is equals to RW, so that's 2 times 5 giving you 10 meters per second straight away. B, that we have find the angular velocity, 120 radians per minute. Now, that's not in seconds. That means we can't find in the seconds yet. So angular velocity is 120 radian per minute. That's equivalent to what? As a per minute, we have a 60 seconds. 120 divided by 60 radian per second. That's a 2 radians per second eventually. So therefore, the velocity is r, the radius of the 5 meter, 5 times 2. So 2 gives you 10 meter per second straight away. C, we have r equals to 50 centimeters and r is 360 degrees. So make sure you convert the units centimeters to the meter. So because we are taking that into the standard units. Yep. So r is 50 centimeters, which is equivalent to 0.5 meter. In this case here, angular velocity was given 360 degrees per second. That's what? That's basically 2 pi per second, which is approximately 6.28 radians per second there. So therefore, the velocity is times these two, 0.5 times 6.28 gives you 3.14 meters per second. Okay, D, that we have the R is 10 meter, then R and W is 1,200 RPM. So 1,200 RPM, again with the same thing, 120 revolutions per minute. So that times 2 pi divided by minute, 60 seconds. Yep.
Radians per minute?
Is radians per minute?
I made this mistake.
Because it says up at the top.
Yeah.
The meters per second.
What's this revolution?
The B, did I convert the radians per minute to
The B
seconds?
is right, but like in the question it says radians per minute,
Yep.
and like D it also says like RP. Was that revolution?
Revolutions per minute.
Oh.
It's not the radians per minute, it's the revolutions per minute.
Okay.
Those same.
No. Rev means revolution for one circle. So it means 2 pi. Yeah, no, like RPM sounds like radians per minute, though. But revolutions per minute. Means that if you have that RPM, that means per minute it has that 1,200 revolutions in that minute. So that's how you get the radians per second. So 1,200 times 2 pi divided by 60, you get 125.6 radians per second. So V is times the radius that we have 10. 10 times the 125.6 gives you 6 meter per second. That's the velocity there. Okay. Well, it's good to know now. The RPM is not for the radians per minute. It's always for the revolution per minute. Okay, 5. A carnival roundabout of the radius 2 meters rotates on the angular speed of the 1.5 radians per second. Calculate the centripetal acceleration of each seat of the roundabout. Okay. Kevin, did you figure out what I said to find the angular acceleration or the acceleration? Not really. Think about here. A is founded by v squared over r, isn't it? Okay. Now, how do you find the angular velocity? Using that relation here. V on r. Oh. Then, can I just substitute that into here? The making that centripetal acceleration is angular velocity times the v. Yeah, or this is same as the square of that times the r. Okay, because as this is v squared over r squared. Okay, so angular velocity times the r is equals to v squared over r squared times r. Cancel the r out. That's a v squared over r. That's giving you a as well too. That's what I mean. Like you have to rearrange the formula. It's either be this one or where is it? Oh, this one. Okay. Again, you would not get those formulas in your formula sheets.
Okay, so if you use that formula for working out, you have to derive it as well.
You don't have to. Yeah.
Wait, then what's stopping you from like using the other formulas?
Because that's a mathematical extension 1 formula.
Well, like if you derived it, then can't you?
No, this is like something we have to teach in the school. Like in physics class. Okay, but we don't teach you how to use that extension 1 mathematical formulas in physics. We'd rather want you to like investigate it, like to get some relation between x and y components. Does it make sense? Okay, that means it's safe to just use that formula, this one, angular velocity equals to v on r, straight away without showing any proof. It's safe to use that. It's verified because we have the same working out given in the HSC syllabus and the working out of the HSC paper. This is safe. Okay. All right. Then once we get up to here, we can consider about how to use this. Then question 5a, that also not a. We're given that radius is 2.0 meter. And angular velocity is given as 1.5 radians per second there. Then, if you know the formula, it's easy. A is simply be angular velocity times the r. That's 1.5 squared times the 2, which gives you the 4.5 meter per second squared straight away. Okay, so sometimes you will forget these formulas. But if you can remember this one and the relation between the acceleration there, you may be able to figure out how to get that. This is the skills required questions as well too. Okay, 6. A motorcyclist rounded a corner of the radius 50 meter at a speed of the 50 meters per second. If the mass of the cycle is a 70 kilo, calculate the centripetal force on him. So to get the centripetal force, okay. First of all, let's determine the angular velocity, acceleration. AC, which is a centripetal acceleration, can be calculated by using this angular velocity squared times the r. Okay, where we get the angular velocity is, we're not given angular velocity, do we? We don't. Oh, sorry. We can just simply use v squared over r. That's it. Easy. It's an even easier. Or we can just simply use FC. The centripetal force is known to be mv squared over r straight away. Show all the substitution required then. We have the given that it's a 70 kilo. It's moving in that 15 square, the velocity is 15 square divided by the radius 15. So I guess cancel 1. So 70 times 15. You should get 1,550 newtons. And centripetal force direction. Yes. Always. Okay, next one, question 7. A satellite is designed to travel in a circular orbit around Earth. The radius of the orbit is to be 7.2 times 10 to the power 6 meter, where it's a centripetal acceleration 8 meters per second squared. Calculate the speed of a satellite. So let's write it down. What we have given the radius. R is given as 7.2 times 10 to the power 6 meter. That's given. Then we also give a centripetal acceleration, AC, that's 8.0 meters per second squared. Think about how we find this. This is founded by V squared over R. Therefore, velocity is founded by 8 times the radius, 7.2 times 10 to the power 6, and square root of that straight away. So that's giving you 8 times 7.2 times 10 to the power 6, and square root of this, you get 7,589. You don't have to fix in a sig fix, but as you're given some sig fix value, which is 2, this is equivalent to 7,600 meter per second in 2 sig fix. That's how fast the satellites are orbiting around the Earth. This is actually really fast. Okay, question 8. A car of mass 600 kilo travels on the circular track of the radius 60 meter. Calculate the centripetal force needed to enable to travel at 40 meters per second. So we have given the mass is given, circular track. Okay, centripetal force needed to. Okay, straight use FC. The centripetal force calculated by mv squared over r, and showed all the substitutions required. For this, we have a car mass is 600 kilo. Times that it's moving in the velocity of the 40, so 40 square, divided by the radius, that's giving us 60. So 600 times 40 square, divided by 60, you get 16,000 newtons. Direction would be towards the center again too. Towards the center. Question 9. A piece of the fishing line, 2 meter long, of the breaking strain of 40 newtons is affixed at the steel ball of the mass 0.5 kilo. Calculate the greatest angular velocity with which the ball could be whirled in a circle before the line broke. Okay, what is going on in this situation here? Has anyone done the fishing? Or known how to do the fishing? Like basically we whirl that. We are kind of rolling that fishing line so we can capture, we can get the fish out of the water. So, breaking strains, and the 40 newtons fixed the steel ball of the mass of this 4.5 kilo. So you can think about here, there's a kind of make it fixed into line, and we try to make it exert some centripetal force in this direction. Okay, so this is kind of rolling. We kind of roll this so that we can get the fish out of the water. So in this case here, we can take, the centripetal force we have to exert from the ball is the same as the tension force that exerted to that. That means that we have mv squared over r, which must be same as the given amount of tension force that we're given. That's 7.28, sorry, I'm drawing the 40 newtons. Okay, and the question is asking you what is the angular velocity of it. So once we get the velocity from here, or we can modify that formula if you like to, because we know the relation between the angular velocity, that A is equals to angular velocity times the radius there. Okay, so we can just think that as, this is actually same as mv squared over r, that's m times the angular velocity times the radius as well too. As the centripetal acceleration is same as v squared over r, that's the same as what? R2. Does it make sense? Okay, so from here, divided by the mass of the ball that we have, let's question that, 0.5 times the radius of the line, that's given a 2, and square root of this. So that's basically root 40, which is 6.32 radians per second. That's the angular velocity required. Question 10. An electron orbits the nucleus of the atom of the radius of the 2 times 10 to the power minus 10 meter. If the mass of the electron is 9.1 times 10 to the minus 31 kg, and the force of the attraction between the nucleus and the electron is 7.28 10 to the power minus 5, calculate the tangential speed. Okay, good. This is what I mean here. When we have a positively charged nucleus inside there, electrons is kind of orbiting around there. And what we have here is, we have some force, which is attractive force. Attraction force between the positive and negative charge. But this case is working exactly the same as the net force value. That's working as a centripetal force. Okay, so two different type of force which is working exactly the same, therefore I'm generating the same motion of the circular motion there. So we're given all that information that we have. That's given 7.28 times 10 to the power minus 5, which is a centripetal force, is equals to mv squared over r here like this. So to find the velocity, it would be the force times the r divided by m and square root of this, which is 7.28 times 10 to the power minus 5 times the radius of that is given as 2 times 10 to the minus 10. Okay, divided by mass of the electron, so 9.10 times 10 to the power 9.10 times 10 to the power minus 20 minus 31, and square root of this. Okay, you can put everything in your calculator, but don't put it into the fraction forms. There's a chance you can make a mistake from it. So if you calculate it correctly, then 1.26 times 10 to the power 8 meter per second is the final answer. Okay, question 11. Have you guys finished 11 yet? 11 and 12? Give you about 3 more minutes to try the 11 and 12. Give it a go. We're going to talk more about the banking. So the meaning of the banking is this. Has anyone watched like an Olympic, like in a cycle? Like in the indoor cycle? So you know, like in it's called a velodrome track, that you see like a track is something like a shift kind of tilted rather than plane. They're kind of tilted there. So you see that cyclist is kind of running through that tilt. So you can imagine that it's kind of coney shape, and they're like running in the kind of velodrome track. So that's what I mean by the banking. So that's kind of giving us situation here, and cyclist is kind of moving in that banking track with the angle theta here. Okay. We also have the banking in chapter 3, but I'm giving you some idea here. Now, when someone's running the banking track, this is something we have to remember here. Without the banking, assume that we have a cyclist, okay, and try to make a circular motion. So it's making a circular motion track like this. It's like you can imagine like in the plane surface, I'm kind of making the horizontal circular motions there. Then in that case, in the plane surface, I want you to imagine about here. I'm making the circular motions. So as I kind of showed you before, I'm applying quite a lot of the friction force on my left foot here, so that I can make a turn efficiently. Okay? Now, if I make a greater force, if I exert a greater force on my left foot, then what happens is I can make a faster turn. Okay? Or I can make like even greater angular velocity. So it's kind of proving that, the greater the friction force applied on my left foot, like this, I'm making the greater centripetal force applied to it. In other words, in the plane surface of the circular motions, we take that as the frictional force you apply onto your pivotal point is exactly the same as the centripetal force that we can have. In other words, greater the frictional force will be greater the centripetal force, which is mv squared over r. Think about what we mean by greater centripetal force, guys. We can determine the centripetal force by, it's because I can't change my mass, I'm not losing my weight or gaining the mass, but greater the friction, the centripetal force means it's either increase in the velocity or decrease in the radius. This is something very important that you have to understand. In other words, centripetal force is directly proportional to the v squared and is indirectly or inversely proportional to the radius there. As I showed you before, if I apply the greater force on my left foot, okay, the faster turn with a greater angle, or the smaller the radius in that case. If you think about it, smaller the radius is much better to making a greater effective spin. The bigger the turn, bigger the radius means it's hard to make effective spins, so that this requires a greater amount of the force too. Yep. I'll show you that in the demonstration next week when with this pendulum. What are the velocity? Greater the centripetal force, obviously, making a faster turn. Therefore, linear velocity getting increased. Does it make sense? This is related to the question 12. Corner. The corner is not banked. The frictional force that the tires of the truck provided to enable it negotiate this maneuver of without skating off the road. So think about the truck which is really heavy. To make an effective turn, the truck needs to exert quite a lot of friction force on the tire. If the truck doesn't apply the much effective like frictional force, you can imagine that truck would not make the good turning. That could be caused an accident, the fatal accident there. So let's do the 12 first of all. Remember this, in any of the circumstances of the circular motions, we take the centripetal force as our net force value. So, using that, you can imagine the mass of truck is, again, truck is the truck driver here. Let's kind of try to turn. And we try to turn here, there's always the force applied to the center. There's a frictional force applied, which is same as the centripetal force that applied. That is same as the net force applied to this truck. Okay, which means 2,000 times round the corner and the radius 50 meters and that. So velocity is given at 30 kilometers per hour. Converted that into the meters per second by times 3.6 or so divided by 3.6. So you get into 8.33 meter per second there. The radius is given as the 50 meter. And mass of the truck is given as 2,000 kg. Combining all that to find the centripetal force, F equals to mv squared over r. That is 2,000 times that velocity, 8.33 square, divided by the radius, 50. then you'd get 2,777.8 newtons towards the center. Which means that this much of force, frictional force, is required to enable the truck to make a turn for 50 meters track. Make sense? All? Okay. I probably just stop here. I will have a chance to go through a question 11, the banking questions, because that requires quite a lot of the understanding about forces. Do you remember the forces acting on the slope? The car is going upwards and downwards. That's the application of that. Means I'm gonna use the normal reaction force in here. But I want you to think about when you're running if you imagine that you're running on the banking track, kind of slanted track. Okay, I want you to think about your body's kind of movement. It'd be good if you can run in down in the skateboard like in the kind of tracks. Okay, you're running inside of that. So your weight or the normal reaction force is kind of helping you to maintain the velocity. That's what we're going to discuss next week. Okay, good. Any questions about angular velocity, how to convert that? There's a bit of formulas required for this.
I got like same. I did the same calculation. I got
Yeah.
2,775.
Add more threes. 8.3333. You get
Oh
like
yeah. Oh.
Yeah.
Okay.
That's that's what we call the sig-fig error, by the way, because when you're using the 8.33, which is just the 2 decimal points, yeah, you get the 775. But when you use the exact value of the converting that, you get the 777. Okay. All right. Any questions about chapter 2 for next week? Okay, give you some homework to do for next week. Yeah, I give it here. This is like some copies of the chapter exercise you have at the back, but I want you to do this for your homework next week. Please pass that.